And they're saying, we didn't do that on theory. There's like,
Oh, I'm not going to be able to walk for sure. Such a great time.
It's way too close on somebody within the show production was like, that was too close. We could change it. So there's no way that they're going to know. As you know, I came out in the very first episode.
I thought you were going to say something like I'm a ninja. Just because I know
I have my grandpa
Zooming into the show.
It's like this thing, and it's not heavy.
You can do it if you want. I'm not going to ruin it. So,
I should have maybe done now.
I was the only person that's doing it today. Like, even though it's
that's what it's called. I promise it's just a term that I grew up with. I never even Shut up.
Okay, as I suspected, the homework there was a high level of success, so we're just going to press on. As always, if you have questions, please come to Owen or my office hours, okay? All right. So let's start with a little review, and it'll bridge us into the next thing we want to talk about. So let's let f be any function. Okay, so in general, just in a very broad sense, what are possibilities for the type of function that f could be? Okay, so yeah, so it could be accumulation, right? The two main kinds of functions we talked about are accumulation, or like just how the quantity, tracking a quantity, or the rate, tracking the rate of change of a given quantity. Okay, so f could be either one, all right? So what is this saying? It's saying if the derivative is greater than 0, or in other words, this means
If the rate is
positive, right? So the derivative is positive, then what can we say about f? No matter what kind of function it is, what could we say about the function f? Okay. Connor, what do you think?
Its rate of change is always positive.
Its rate of change is positive. Okay, well.
Well, it's always going to be increasing.
Increasing, he says.
Yes.
Agree with that? Lots of people agree with that. That's right. Okay? So if, no matter what kind of function it is, if its derivative is greater than 0, or an interval or at a particular point, then that function is increasing on that interval or at that point. Okay, so let's take a step back. Prove it. How do you know that it's increasing? Okay? I'm not talking about the graph here. What I'm talking about is how can you reason about the quantities, input x and output y? How can you reason about those quantities to prove or show this conclusion that if the rate is positive, then, or if the derivative of f is positive, then f is increasing. So why don't you have a conversation with someone next to you? Should be, so. How would you reason about the quantities x and y? to prove this. Okay, Dan, can you get us started here?
I was thinking that the change in y is going to be larger than the x, the change in x.
Okay, so the change in he wants to compare the change in y with the change in x. Does showing this have to do with changes in y and changes in x? You want to say some more?
Oh, no.
So,
On the right track.
okay, well, he's talking about changes. What do you think? Andrew. Yes, Andrew. Want to add to that or start again? Or?
Well, I was thinking that if df dx is positive,
Right.
that means the slope of f at that point is increasing.
Okay, so you're kind of getting to the graph. Yeah, so that's true. But I wanted you just to reason about the quantities x and y and not the graph. That is true. Somebody else? Sharon?
The rate of change is also the relative size of delta y.
Okay. So this is the relative size. And how do we express relative size?
Delta y over delta x.
Okay. Oh, sorry. I don't know what I'm doing it down there. Okay, so she's talking about this number k, that if this is really our number k. Okay?
And then delta y equals k delta x.
All right, so for so can we start out with a small delta x? So for a small delta x, she says delta y equals k delta x, okay? So what?
Delta y is a multiple of delta x.
Okay.
So if k is positive, and then delta y is
So if k is positive, because k is this is our df dx, right? So how do we know that f is increasing? Corey, you want to take it from there?
I mean, it just, like, that goes back to the graph. Delta y is going to continue to get less negative or more positive as it goes as x, just depending on where it is on the graph.
So what do we got here? So we got delta x, positive or negative? No, we're in charge of delta x. We always make delta x what? Small little increase like this, right? It's always a little increase like this. We could make it a negative change, but so we're in charge of delta x. And delta x means a little change or a little increase, okay? So what about delta x? Positive. What about our k? So what about delta y? Positive. Okay, so what does this show about the function f? The change in y is positive. The change in y is positive. So therefore f is increasing, right? So for a little change in x, if delta y is positive, then y just went up. So the function's increasing, right? Function's increasing. Okay, now let's talk about the graph. So if f is, it's just an accumulation function. What does it mean for the graph of f? The accumulation, to say that it's increasing. So we're saying now this is just some accumulation function f of x. And we're finding that the derivative is positive, and we're concluding that, therefore, that accumulation function is increasing. What does it mean for the graph? Adelaide. Okay, no problem. All right, so we're talking about, we just said that if the derivative of any kind of function is positive, then that function is increasing. So now I'm saying that we want to pick an accumulation function, just any quantity function that we want. So if its derivative is positive, then that accumulation function is increasing. What does that mean for the graph of f, the accumulation function? What's that? Yeah, so what does that mean for a graph if the function is increasing? Someone said positive slope. Yeah, David. Getting steeper. Does it have to be getting steeper? Just has to be going up. So it doesn't. So here it's getting less steep, but it's still increasing, right? So this is what an increasing accumulation function is like. It's going up. It's going up from left to right. Okay. Good so far? So now what about if that f is a rate of change function? So now we have this accumulation function f, and we have its rate of change. And this is the function whose derivative is greater than 0. So we said that if that's true, then this thing's increasing, right? So the derivative of the rate is positive, therefore the rate is increasing. What does that mean for the graph of f if its rate is increasing? What does it mean for the graph of f if its rate is increasing? Thoughts on that? Okay. But now I'm talking about the graph now. So what would the graph be like? The slope is getting larger. Steeper. So the slope is getting steeper. What do you think? So draw it with your finger. Okay. So what I saw him draw was this.
Yes.
Is the rate increasing? Is the rate increasing here? No?
No, because it's negative at the very beginning.
Down here.
And you said the graph of f or is that
This is f. F. What does it mean for the graph of f?
okay, well yeah, then the rate is increasing even if the bottom is negative. The slope is still positive.
Is the rate increasing here?
Oh, yeah.
This is f, not the. I'm not drawing the rate. I'm drawing the accumulation.
Yeah.
So is this it? This is all that it means for the graph if the rate is increasing. Stanley, is there more to talk about?
Think about it. It seems like that's true.
It's true. It's true. Is it guaranteed that the graph of the accumulation will look like this if its rate is increasing? Talia?
I would say over that interval, yeah.
Okay.
The steepness depends on the rate of change and rate of change.
Okay.
Yeah.
Yeah, Daniel.
Yeah, we don't know that it's the rate is increasing at a constant rate. It could be increasing by more than increasing by less.
Okay.
It's not a change how quickly it is zero.
Okay. So what's true about the accumulation that we've drawn here? Just the function f. its rate is increasing, but we've also made the assumption what? Just simply, what's the accumulation doing here?
Gradually.
It's increasing, right? Is that a requirement for the rate to be increasing? Could the accumulation be decreasing and the rate increasing?
Yes.
What would that be like? Some people are drawing this.
Finish out the curve.
Okay, so over here, is the rate increasing? Is the rate increasing? So I'm trying to draw some slopes here. There's a slope. Now as we move, increase x. Here's the next slope. Here's the next slope. Let me see if I can draw one more. What are the slopes doing? What's the rate doing here? Increasing or decreasing? So maybe this rate of change is -3, and then this one is -2/3. This one's -1/2, and this one's -1/5. Are these numbers increasing or decreasing? These are increasing rates. Why? Because the rates are getting less negative. So, in general, if you know that the rate is increasing, you don't know if the accumulation is increasing or decreasing. It could be either. Could be either. All right. If the rate is increasing, then the rate is either getting less negative or more positive. Both of those are increasing rate. Less negative rate or a more positive rate. So what then is the conclusion? We can't conclude that the accumulation is decreasing or increasing, but we can say that the accumulation has what kind of shape? This is about concavity. This is what we call concave up. Okay? Concave up. So if the rate is increasing, it's always concave up, whether or not the accumulation is decreasing or increasing. That rate is always increasing. And so the shape of the curve results in concave up. Okay. Any questions? Let's do it again. So now, f can be any function, accumulation or rate. If the derivative of that function is less than 0, then what can you say about f? Decreasing. How do you know? Tell your neighbor. Go. How do you know? If the derivative of anything is negative, how do you know that whatever that function is decreasing? Okay, I'm gonna call on some of you, and I'm expecting great things. So make sure you understand this. Okay, and this question is not about the graph. I want you to reason about the quantities x and y. Reason about the quantities x and y. Okay, Daniel, number 2. Tell me. Okay, for a change in x. Okay, so for small delta x. And how do you know that? How do you know there will be a decrease? Okay. How does it? Right. Okay. How does it make the change in y negative? Because change in y is what? Right. And what is k in this case? Times? I should really say about. Okay, so this is our k. All right, keep going. So you're almost there. Putting it all together. K is negative. Right. And so if the change in y is negative at whatever value of x that we are, then what is f doing? Yeah, if the change is negative, then y just went down. It decreased in value, so the function's decreasing. Okay, so let f be an accumulation. What does it mean for the graph if f is decreasing? Somebody new? Eric. So this is an accumulation function. We're going to call it f of x. And we just found out that its derivative is negative, and we conclude that f is decreasing. So what about the graph?
The graph is about the average. Its slope is negative.
Slope is negative. And so if the slope is always negative, in general, DJ, going down from left to right. Heading down from left to right. Any questions? Okay, so then the more interesting question. Now f is our rate of change for the accumulation f. What does it mean if Rf is decreasing? So we found out that the derivative of the rate is negative, therefore the rate is decreasing. The derivative of the rate is negative. Our conclusion is that rate is decreasing. What does that mean for the graph of f if the rate is decreasing? Christina? What's that? The slope will be decreasing.
Yeah.
So you're drawing with your finger, you're drawing something like this.
Like from the y-axis,
Like that?
yeah.
Agree? Autumn?
Excuse me, the other half would be in quadrant 1 going this way. Because it starts like at infinity and then
Yeah.
it's decreasing. Right?
Okay, so is that a decrease? So you're drawing like this. Is this a decreasing rate?
It's an increasing rate.
That's an increasing rate, right? Yeah, because it's getting less negative, okay? So we want a decreasing rate. Is there another way? Yeah, Jacob.
Anything in front of your face?
Okay.
Okay, down.
That's how I learned it. This is front of face.
Okay, so see if I can draw some slopes here. That's a good one. Oh, 2 for 2. What are this? Oh, 3 for 3. It's your lucky day. What are the slopes doing as x increases here? The slopes are less positive. The slope, the rate of change The rate is becoming less positive. Okay? What about over here? What are these rates doing? Is the rate increasing or decreasing? Well, is the rate becoming more or less, negative or positive? More negative. Therefore, decreasing. If this was a speed, if this was distance of a car, the red graph, then our rate would be speed, right? What would the speed be doing? Increasing or decreasing here? Speed. Yeah, okay, that's a bad question. All right, so less positive or more negative all means decreasing rate. So what does it say about the original function f? Whether, okay, yeah, so whether or not that original function is increasing or decreasing, concave down. Jacob, like a? Like a frown. All right. Concave up, like a? Someone's going to get it. Concave down, like a frown. Concave up, like a?
Has to rhyme.
Like a clown.
It's
Up.
I win.
Who said it? Tyler. Okay. Yeah. So concave up, like a cup. Concave down, like a frown. Okay? But more importantly, that's just a little trick to help you kind of remember what we mean when we say concave down. But more importantly, concave down is when the rate is decreasing. And you should understand the rate is becoming less positive or more negative. Okay, any questions? Okay, so there's a lot to keep track of there. So every individual question may have made sense. But now to assimilate all that and to organize it so that you can answer questions where lots of things are coming at you at once is the challenge. Okay, so one thing we've been talking about here is this idea, the derivative of the rate. The derivative of the rate of change of x. Okay, another way to say that is the derivative of the derivative, right? The derivative of the derivative. So this is called the second derivative. And what is it about? Well, we were just talking about how the rate is changing, right? This gives us information about how the rate is changing. How the rate is changing. Is the rate increasing? Is the rate decreasing? Okay, so there's other notations for this that you'll see. These are more common notations. They all mean the derivative of the derivative, or the derivative of the rate of change function. And they give us information about how the rate of change is changing. Okay, so y double prime, or f double prime, is what we say. Okay. So what I have is, we're going to kind of put this all together. There's these combinations of, if we know information about the first derivative and the second derivative, can we put them together to make inferences about what the accumulation is doing? So this is what this activity is about. So coordinating information, are there enough in the back? Okay, coordinating. Coordinating information from the first and second derivatives. So we'll do this first one together. The first derivative is positive. So what you're doing here is you're making sketches regarding the accumulation function, or the original function f. Okay? Can you sketch the original accumulation function if its first derivative is positive and its second derivative is positive? So the first derivative of accumulation is positive. What does it mean? So this is all the stuff we just reviewed, but there was lots. So what is going on with that function if its first derivative is positive?
The rate is increasing.
I heard concave up, I heard increasing, I heard the rate is increasing. See, it's confusing, right? So you gotta file it away. All three of those are correct. If the first, now all I'm asking is if the first derivative is positive. That's all I'm asking.
Oh, no. The rate, no, sorry.
The first derivative is.
And begs, yeah, that would have to be, if that would be the first box.
I'm asking about the first derivative being positive.
Concave up.
Concave up. What do you think?
It's a line that is increasing from
Not a line. Lines are straight.
a slope that is
Okay.
increasing, but it's not exponentially.
Watch your. So we've got to be really careful with the language. You said the slope is increasing. Is that what you mean to say?
No, the
That's not-
accumulation is increasing.
The accumulation is increasing. That's all the first derivative positive means. Accumulation is. So the graph is
Increasing.
going up, increasing, increasing. That's all it means. It means the accumulation is increasing. Okay. Now also, the second derivative is positive. What does the second derivative positive mean about the accumulation? What's it? So it is a four-letter word. No it. There's so many things going on. So the rate is becoming more positive. Sharon, agree with that? What's that?
The rate is becoming bigger.
The rate's becoming bigger. So the accumulation is becoming bigger. It's increasing. And the rate is becoming bigger. What will the accumulation look like when those two things are true? Draw it with your finger. Watch out, Beth. You're going like this. So what will it look like? Do it. If the accumulation is increasing and the rate is increasing. There you go. Does it make sense?
Yes.
Okay, go. Take 5 minutes and see how you can do on this. Okay, so no linear functions. Okay, no linear functions. All of them are curved, right? All the functions that we want to analyze, or that we're talking about here, is curved like this.
So he just said there's not really any
So, analyzing a function like this. Analyzing a function like this. Not linear. Okay, keep going.
For first derivative.
this way or is this one really
First derivative is positive.
Oh, no, I'm talking about first derivative is 0.
Oh.
Not.
I don't know what is this. You can't have it cancel.
It's basically first derivative. So the first derivative is positive, that means the accumulation is increasing. Okay. Second derivative is 0, means that the rate
The second derivative is 0. Sorry, the second derivative is 0. It has to be positive.
What's that?
The second derivative is 0. Isn't it?
Nope.
There's no change in I guess
So it could be the second derivative out of a different.
Like maybe locally, okay? Yeah. So Connor. So locally, yes, okay. But I'm just saying you don't have a linear function.
so it's
All right. So we're looking for components of this that make them all true. Does that help?
So would it be like this? Like, blah, blah, blah.
Oh, these ones
Or would it just be at the top? Sorry.
This is
Why don't you just say, don't tell me everything? No, that's like, look at it.
These are all
imagine like
I'm just gonna drop it. And then the second derivative on x, the second derivative is 0. I mean, it's a negative.
Definitely going.
Yeah, this one I might be wrong. This one is
I think it just changes. What's the opposite of the first?
Would it be like this?
Yeah, he said that if it's 0, it can't be second.
I wouldn't be this way.
Is that accumulation? Which were this way?
It's this.
Your accumulation is not distance.
You just have
Your accumulation is still increasing.
You have it on
The grammar.
1 to 3 to 4.
Right?
I don't really understand. Don't understand graphs at all. Yeah. So it'd be like y equals 6. Take the derivative of that, it would be 0. So it should be straight line, flat.
coming from
Derivative
for the second derivative.
That's what I had in my head too.
Oh, 0.
those points.
It should be the,
Be the rounded part.
yeah, I think so. Like the tangent is that right? It's, or at the very top.
Fine, you're in the fine.
The second derivative is 0. First derivative.
Oh, it's the second derivative is positive.
Okay, I'll give you a hint. So some of these things occur over intervals. You can show it over an interval. But some of them only can occur at a single value of x and not an interval. So the ones that you may be stuck on, you're trying to think of an interval where it works, but it won't work over an interval. It'll only work at a single value of x. Maybe that'll help. Okay?
I think this is what I'm saying about this one.
So
Because you're talking about accumulation something like, the accumulation function is like this, right?
First derivative is 0.
Or,
Down.
what am I saying?
0 positive, yeah.
Yeah, whatever.
The
Anyways.
second one can.
Or it would be like this. So this, and then you take the derivative of this, but it's,
So
and then
what
we're on
does
this
it tell
whole
you
thing,
about
it's
this?
flat.
Derivative is 0. First derivative is positive, it tells you that the accumulation
So it's
is.
the very, like the
Increasing.
little,
If the first derivative is negative, it tells you the accumulation
that's
is.
where it
So the
is.
first derivative is 0.
I was just gonna write local max.
it's like flat.
The constant is this? As x changes,
Just draw a tangent.
it's this?
I mean,
No.
it's not increasing.
That's the opposite of constant, right?
So it would be that tiny little
So what?
You know that? Okay. So what does it mean for how y is changing this way? What does it mean for how the accumulation is changing as well? 0 to 0. What does this mean for how the accumulation is changing?
He said this one. I thought he said that you said
Yeah, so it's increasing, right? So accumulation is increasing. What does this mean? Here you're showing that as x increases, you're showing the accumulation is going up, right? First derivative talks about how the accumulation is changing. It's positive, accumulation is increasing. Negative, accumulation is decreasing. Is it decreasing? Okay, if the first derivative is negative, what does it tell us? Chelsea, just if the first derivative is negative, that's all I want to know. What does it tell us? What's it? Accumulation is decreasing, so what does that mean for the graph of the accumulation? Going down. So in this box right here, it's going to be somehow going to be going down. So how will it be going down if the second derivative is positive? Talk to me about what the rate is doing, Adonijah.
The rate is becoming less negative.
The rate's becoming less negative as the accumulation goes down.
Yes.
I like that a lot better. Yep.
So like a cup is not an acceptable answer on a test.
It's just, the only thing that's for is helping you remember what concave up is.
Okay.
But how the rate is changing and how that compares the derivatives is much, much, much more important. Okay, so here we really have this interval of the graph, do we not? From about here to here, right? So this first part is which? First derivative is negative, which means the rates are, what are the rates doing? The rates are increasing because they're becoming what? Less negative. And then the rates become positive and increasingly positive. Okay? So through this whole interval, we have increasing rate of change, starting with accumulation decreasing, then accumulation increasing. So the accumulation is decreasing, and that means the first derivative is negative. And then the accumulation is increasing, meaning the first derivative is positive. So how does the first derivative change from negative to positive? Right there, what happens? First derivative is, what does the first derivative 0 mean in terms of the quantities x and y? What is constant? What's happening? What's that?
There's no change in y to y.
There's no change in y. So, first derivative is negative, and then for a moment, the first derivative is 0, and then it turns positive. So, for a moment, that first derivative is 0, and so we have that changes in y, approximately k delta x. For a moment, k is? So what about delta y? 0. So for a very small delta x, right there for a moment, when that rate of change is 0, it's like the value of the function pauses, right? It pauses, or it doesn't change. There's no change in y at that moment. So what does it look like if the second derivative is positive and the first derivative is 0? That whole thing? No, just a single point right there. Lowest point. But so why that's true is really important. What about the second derivative at that lowest point? 0? Second derivative is 0. If the first derivative is 0, then the second derivative has to be 0. Agree?
Yeah.
Tyler, talk to me.
At that point, you're going from having more negative slope to having more positive slope. So it's, as you're going through that point, it's changing. Doesn't say
What's it?
the rate of change.
Rate of change is?
It's going from more negative to more positive.
Right. Didn't we say that the rates over here are becoming less negative? And then we said the rates are becoming more positive.
You have to take it over an interval rather than take it at the point, this section.
Okay, great. Over this interval,
But over the interval over which that curve is.
are the rates increasing? Yes. So, is the second derivative always positive through there? Are the rates always increasing through that interval? The rate is becoming less negative and then more positive. So, here's what the rates do, right? Here, this is what the rates do. This is what the rate does. So, because the fact that the rate went through 0, does it mean that it stopped increasing? No, the rate was increasing the whole time. Therefore, second derivative is positive through all those values of x. So, is the second derivative 0 even though the first is? No, it's positive. The second derivative is positive because the rates are increasing through that whole thing. So this is a common misconception students have. If the first derivative is 0, well, the second derivative has to be 0. No, the rate is increasing through that whole interval. The rate's becoming less negative. It's 0 for a moment, then it's becoming more positive. Constantly increasing, or continually increasing, the rate is.
So are you talking about just the lowest point or the figure as a whole?
Both. I mean, what about just this point? What about just this point? Is the rate increasing? Would you buy that? What about just this point? Is the rate increasing? Okay, what about the very bottom? Is the rate increasing?
It's still, this is the lowest form. It's only because the value of k is going to be 0, not because the entire function k is 0. I'm sorry, the entire function.
Yeah, see, yeah, exactly. The rate is becoming less negative. For a split second, the rate is 0, and then the rate's becoming more positive. So that rate is continually increasing. Second derivative is all positive through there, so therefore it's positive at the bottom.
But if we're dealing with it in like a closed form type situation, then it would be zero, would it not? Because if you're taking the first derivative and it's zero, and you take the second derivative.
No, but so you have the first derivative, it's a function. When you put that x value in, the first derivative gives you 0. Now you take the derivative of that function, you get a second derivative. When you put that x value in, you don't get 0 in that. So you don't take the derivative of the, so you're thinking about taking the derivative of a constant function 0. That rate is still a function of x. You plug in that value of x, it gives us 0. Then we take that rate function, we take the derivative again, plug in that value of x, now it's going to be positive. You see? Okay. So, so with that in mind, now I want you to, as part of your homework for Friday, I think hopefully the corners are a piece of cake. You can reason about the corners and get those shapes exactly right. It's these ones that have more to think about now that we've talked about that. So as part of your homework for Friday, you should take your time and think through, reason through what would have to be true for the remaining 5 boxes here. That's not the only homework, okay? But so there will also be more on Blackboard. Be ready to possibly turn it in. Next couple days. Yeah. Last year I didn't do that. I just gave you whatever you got. But that's not to say I might change it this year.
You suck.
You can get it done.
I've only missed 2 classes. I only had to show up 3 times.